In section 3.6, we're going to talk about another new important derivative rule known as the chain rule. Now, we already talked a little bit back in our section on the quotient rule about why we might need, or situations where we might need an additional derivative rule. And it's a situation kind of like what we have in the motivation below. Suppose I wanted to find the derivative of a function like f of x equals a quantity, 2x plus 1, all to the third power. Again, if I was to go through and take a look at any of the derivative rules that I already have available to me, I can see that none of these derivative rules seem to apply. My constant rule doesn't seem to work here. I don't have a function just times a number. I don't have x raised to a power. I kind of have like a whole separate function raised to a power. And I can see that definitely my sum and difference rules don't apply, my product rule doesn't work, the quotient rule doesn't work. And so we need another rule known as the chain rule. Now, to understand a little bit about how I could start to think about this derivative, I should notice that it is actually possible for me to get to a derivative of a function like this if I first take a more tedious route. So I'll even start to state that here. And I'll state that one tedious way to find this derivative would be to multiply out 2x plus 1 to the third power. That is, actually write this as 2x plus 1 times itself 3 times and do all of the associated distributing that goes along with this. And of course, once this is done, you could imagine that I'm probably just going to have, a big long polynomial, right? I'm going to have x's raised to powers added to other x's raised to other powers. Now, actually, if I was to do this, you could actually confirm that, as I state here, that we can note that if I was to do this process, I would actually end up with the following polynomial. I'd end up with 8x to the third plus a 12x squared plus a 6x plus 1. And again, if you wanted to double check, all you'd have to do is just actually multiply out all this stuff. I'm going to avoid doing that here in this video, but this is the final result of what I would end up with. And of course, if I have that as my value of f of x, then it does become much easier to take this derivative, right? Because I can just use my power rule and my sum rule. And I'd end up with something like 24x squareds plus 24x's plus 6, and then the derivative of the 1 would just be a 0. So this is one, again, possible way to actually take this derivative, but again, it's rather tedious, right? I mean, it's a little bit annoying to do this because what if that had been, say, a 30th power? Then there's no way that I would have wanted to possibly multiply these out. That would have been a lot more work. So we're going to go ahead and take a look at this small case where we have this derivative here and see if we can notice anything about the derivative that we have and the original function, and maybe a comparison that we could make between the two. So as I'll state down here, very interestingly, we can see that f prime of x could be slightly rewritten. If you look at all the terms here, you might notice that there's definitely a 6 in common between all of those. And so I could rewrite this as 6 times the quantity of 4x squared plus 4x plus 1. And if I wanted to, I could actually factor that remaining set of parentheses as well. And I could write this as 6 times the quantity 2x plus 1 squared. If you do 2x plus 1 times a 2x plus 1, you generate this 4x squared plus 4x plus 1 quantity that we have here. And I'm going to go ahead and actually write one final rewrite here. And I'm going to go ahead and notice that 6 could be rewritten as 2 times 3. But instead of writing it like that at the front, I'm going to go ahead and write it like this. That is, I'm going to leave the 3 multiplied in the front, and I'm going to put the 2 multiplied in the back. Now, of course, I'm totally free to do this because I just have multiplication of 3 items here, and so their order in which they're multiplied doesn't matter. But now becomes a really interesting moment. Can I see a connection between the original function and the way that I've written my derivative? Can you spot any similarities? Well, you might see a couple different things. We could maybe start to see that it looks almost like I did something like a power rule here, right? Because I had a quantity, I had a bunch of stuff raised to the third power, and it looks like here I have the 3 come down to the front and the power still lowered by 1, almost like power rule. And then I have to just account for this extra 2. But can you tell how this extra 2 relates to the stuff that's inside the parentheses? Well, it's actually the derivative of the stuff that's inside the parentheses. So we might notice that if we let g of x be equal to x to the third power, and h of x be equal to 2x plus 1, then f of x, our function up above, is actually or can be written like a composition of functions, much like what we talked about on skills check number 2. I can see this as a composition. This looks like the function h got plugged inside of the function of g. And so then when I take a look at its derivative, I can see that what it looks like actually happened here is that in order to take the derivative of f, I started by kind of just taking the derivative of g, of this kind of outermost operation. So I kind of had a g prime. And that g prime would have been like a 3x squared. But notice that my derivative didn't have an x squared. It still kind of had that h of x formula plugged in place. So I have the g prime formula, but just with the h of x still remaining on the inside. And then I kind of follow up with the derivative of that h of x function sitting on the outside. So I'm doing the derivative here of the outermost function, leaving the inside alone, and then I take the derivative of that inner stuff. So this idea leads to what we call the chain rule, and it's written or summarized here in the theorem below. Suppose that g is a differentiable function at x, and f is differentiable at g of x. Then suppose that I'm going to start to work with a function, let's call it capital F, that's built from a composition. Then, if I want to take the derivative of that larger function, the way that I do that is exactly what we stated here. I first take the derivative of the outer function, leave the inside alone, and then follow up with the derivative of the inside. In Leibniz notation, we would actually express it in the following way. Now, this can be a very confusing rule, at least to look at and read, and it's probably the hardest rule to put into practice because it requires that we make kind of a visual switch in the way that we look at or read different problems and look at different functions. But the biggest thing that I can try to help you with, at least at the start, is to recognize that whenever we're working with the chain rule, the purpose of the chain rule is that it helps us take the derivative of functions that are written as compositions, where I have one function plugged inside of another. And this is why in the skills check, we said that it was so important to be able to start to look at functions like this function here and see the composition, to see that 2x plus 1 was being plugged inside of another function, x to the third. And so we'll go ahead and practice implementing this idea and this very specific rule, the chain rule, in many of the examples to come.